Welcome, I'm Rob Frohne, KL7NA.
Hi, I'm Caleb Froelich, and I'm a senior electrical engineering and mathematics major at Walla University.
I'm Konrad McClure, a senior engineering student at Walla University with an electrical concentration, and also the president of the Walla University IEEE student branch.
Hi, my name is Joshua Silver. I'm one of the engineering students who had the privilege to design a software-defined radio for my electronics class at Walla University.
Hi, I'm Jordyn, and I'm also a fourth-year electrical engineering student at Walla University.
Last spring quarter, my Engineering Electronics 2 students at Walla University were all online. Classes were virtual. They were all at home. This class always includes a big design project. So last spring quarter, my students in teams of 2 designed and built literally homebrew software-defined receivers of the QSD variety. Today we're fortunate to have 4 of my students here to describe, give a trailer essentially of their paper, which includes a simple theory of how a QSD receiver works, a comparison of 4 different QSD receivers, and a host of tips and tricks and lessons learned when they designed their QSD receivers that should be of interest to anyone doing anything similar in the future. With direct down conversion, DDC software-defined receivers becoming so popular these days, you might think that the QSD variety is old-fashioned, kind of like the soft rock. But it's enjoying a surge in popularity thanks to Guido, PE1NNZ, and his QSD transceiver design. If you haven't seen his design, you really need to check it out. It's open source, it's on GitHub. It features 123 dB blocking dynamic range, 50 dB opposite sideband rejection, a final amplifier that's Class E, very efficient. This thing runs on single sideband and the other modes. And the whole thing is done in an Atmega 328p running at 20 megahertz. Recently on groups.io, a posting said of one of the SMD versions, quotes, makes a KX2 look positively elephantine. The work my students did on their receivers is directly applicable to transceivers like Guido's, and I'm hoping this group will benefit from my students' hard work.
We're going to dip into the theory first so that we get some terms and basic understanding set for what the paper goes over. We want to make sure that we all have a basic understanding of mixers and quadrature signals. Once we understand that, we'll be able to figure out what I consider to be the hardest line of the title of our paper, using quadrature sampling down conversion, which just sounds like a bunch of techno mumbo jumbo if I've ever heard it. In our paper, we use an analogy for talking about mixers and quadrature signals in a way that most people should be able to relate to. If you've ever seen a video where the propeller of a plane starts up, you may have noticed that it appears to spin in one direction, stops for a moment, and starts spinning in the other direction. This phenomenon, and the reason it happens, works well as an analogy for what we're doing. So in our example, let's take a single blade of our propeller as it spins. We're going to do 2 things with it. We're going to set up a camera to take pictures of the propeller at a rate that we set, and then we're also going to plot a graph of the vertical position of the tip of the propeller as it spins. In this example, we'll spin the propeller at half a rotation per second and take 3 pictures per second. The line on the graph plots the vertical position, and the small images along it show what the camera saw. So let's look at the resulting images. If we flip through our images at the rate we took them, similar to a flip book, the propeller would appear to spin. From these images, it takes 2 seconds to complete 1 rotation, so we would conclude the propeller was spinning at clockwise at half a rotation per second, which it was. There are 3 interesting cases to consider regarding the rate of the camera. If we took pictures at the same rate the propeller was spinning, the propeller would appear stationary when we flip back through it, reaching the same position at the moment we take the picture each time. If we took them slightly slower, the propeller would get all the way around and then a little bit further before we take the picture. When we flip through, as we can see in the small images here, it would appear to turn clockwise slower than the real rate. Here, 0.2 rotations per second. And then similarly, if we took pictures slightly faster, the propeller wouldn't quite get all the way around. And flipping through afterwards, we'd see the propeller moving slowly in the opposite direction, as we can see in the little images here. Here, counterclockwise, opposite to the real thing, at 0.2 rotations per second. So that's where we get the phenomena from a video of a propeller. The propeller starts spinning slower than the camera, reaches the camera rate, and then exceeds it. And so we'll go through those 3 stages and we'll see that slow down and stop and reverse. So that brings us to mixers, because a similar thing is happening. Put it simply, an ideal mixer takes 2 sinusoidal inputs and will output a signal that contains frequencies of the sum of the input frequencies and the difference of the input frequencies. The latter of the two, the smaller one, is the one we're interested in listening to. And this new, slower frequency is known as the intermittent frequency. This change from a fast real rate to a slow apparent rate is where our paper gets the down conversion in the title. We're converting a fast radio frequency down to a slow intermittent frequency that our sound card can process. To connect with our analogy, the propeller rate is equivalent to a radio frequency, and the camera is a local oscillator, which sets our sampling rate. And from sampling the radio frequency at that rate, we'll come up with an apparent intermittent frequency. That is the difference of the radio and the local oscillator, RF minus LO. So there's 2 issues we're going to run into that we have to overcome: images and harmonics. So for images, an important note regarding them is that if a radio frequency is lower than LO, remember RF minus LO, the resultant frequency will be negative. A negative frequency here can be considered to be identical to the positive counterpart. At least on its own, we can't tell the difference. So if we pick up 2 frequencies that are the same distance frequency-wise from our local oscillator, both will appear at the same intermittent frequency after the mixing. So we need to be able to reject the undesired image frequency so that we don't hear 2 stations at once. With our propeller, we can see this if we take images at 1.2 times per second and then have 2 propellers, one spinning 0.2 slower, one spinning 0.2 faster. After our image taking, we can see that the vertical apparent trace looks exactly the same, and the only way we can tell the difference is because of our camera, where we can see the top one is turning at a negative counterclockwise rate, and the bottom turning at a positive clockwise rate. From this, we can conclude that if we want to be able to tell the image and desired frequency apart, we need to track the horizontal position as well as the vertical. That way we'll see that same kind of rotation. So here we get into quadrature signals, which are simply 2 signals that are out of phase from each other by 1/4 of a cycle. If we track both the horizontal and vertical positions, we'll see something like these here, where despite the rotation direction, the vertical position remains the same here, but the horizontal position below is mirrored. Because of this, the stationary vertical graphs are called the in-phase component, and then the bottom 2 are the quadrature components, because they are 1/4 of a cycle out of phase with the in-phase one. So if we put those 2 on the same graph, that can be seen easily. On the left, we can tell whether it's a positive or negative frequency based on the order of whether the horizontal and vertical traces reach, which one of them reach their peak first. With the propellers shown reaching the upmost and rightmost positions in that order will mean it's clockwise, and the reverse will mean it's counterclockwise. Putting those all on the same graph, all 3 iterations, on the right here, we can see that a quadrature signal will lag the in-phase for a positive frequency and will lead the in-phase for a negative frequency. Knowing this, the software-defined radio can determine whether it's looking at a positive or negative frequency, the desired or image frequency, and choose whether to play or reject that audio. Okay, now the other big issue is harmonics. There are an infinite number of harmonics that will create the same traces as the one we're intending to listen to, as can be seen here with one example where 5 and 9 rotations per second when capturing at 4 will get that exact same apparent trace, and quadrature signals aren't going to help with that. This is actually the part where I'm going to tease you, because the reasons for this and how we must address it are left in the paper. That way my teammates will still have time to talk here. If this section went a bit fast, I certainly recommend giving the paper a read, as we've broken things down a bit slower and in more detail here. So now I'll turn it over to Caleb, who's going to go over the designs we discussed in the paper.
Let's look at the highlights of 4 different QSD receiver designs, 2 by student teams and 2 by our professor, Dr. Rob Frohne. We'll run through the designs quickly, highlight their main feature, and then take a few minutes to compare design differences. The main feature of Design 1 by Caleb and Konrad was the instrumentation amplifiers that took the difference of the quadrature signals from the Talo mixer. Jordyn and Josh's design used a differential amplifier and had switchable bandpass filters for a wider overall range of frequencies. Our professor, Dr. Rob Frohne, designed circuits 3 and 4, the distinguishing factor of Design 3 being the use of a doubly balanced sampling mixer. The highlight of Design 4 is the ability to do digital signal processing right on the receiver board. This design follows Guido Tindall's QSD transceiver design. However, Design 4 is only a receiver and has provision for porting the code to a blue pill STM32 board. Let's compare these key design differences. First, the bandpass and low-pass filters. What separates different bandpass filter designs? Quantity and type of filter. Design 2 uses a switchable Bessel bandpass filter with 4 bands, which improves performance by better eliminating spurious signals and reducing the overall noise, whereas Design 1 has a fixed bandpass filter. The pure minimalist, however, would avoid using a bandpass filter at all, as in Design 4, which is easier to make, maintain, and fit on a small board. While a bandpass filter is optional, the low-pass filter is essential. It guards against aliasing and sets the bandwidth of the received signal. The designer can choose the number of poles to use. In Designs 3 and 4, just a single pole of filtering is seen on the op-amps after the mixer. However, an extra pole of attenuation is obtained from the sampling capacitors, functioning as an RC low-pass filter with the resistance before the capacitor. Design 1 and 2 used a separate second-order low-pass filter in addition to the pole of attenuation obtained by the sampling capacitors to improve the modularity of the design, achieve slightly better control of the filtering, and split the gain across multiple stages. Generating a local oscillator signal can be accomplished with a Johnson counter. By using 2 D flip-flops and a clock input, the gray code sequence 00, 10, 11, and 01 can be obtained. This approach was utilized in the first 3 designs. However, in Design 4, the capabilities of the SI5351 were exploited, and using the EtherCAT Arduino library, the same sequence was generating using just 2 clock outputs. It's slightly more programming, but it saves money and precious board space. Many different mixing topologies can also be used, but our designs utilize just 2, the sampling mixer and the Talo detector. The Talo mixer is very similar to the sampling mixer, but samples at 4 times the local oscillator frequency and only produces the difference frequency between the RF and LO signals. Our research, here cited in a quote by Michael Sower, shows the Talo mixer to be one of the most effective mixers available. Our designs helped to validate this, as the image rejection was nearly twice as many decibels in Designs 1, 2, and 4 as it was in Design 3, which utilized a sampling mixer. The difference in amplifiers really all comes down to input impedance. The input impedance has a great impact on the whole circuit. For instance, a large input impedance allows the sampling capacitors to hold the charge longer and makes the amplifier resemble a voltage amplifier rather than a trans-resistance amplifier. The high impedance input of the instrumentation amplifiers of Design 1 is due to the internal structure of the amp and offers several key benefits. 1. It isolates and decouples the circuit into modular blocks, allowing for easier understanding, diagnosing, and testing. 2. It removes the antenna impedance from the gain equation so that only one resistor sets the gain. Now, granted, instrumentation amplifiers are very pricey and fewer options are available. A differential amplifier like that used in Design 2 is cheaper, and in our testing, we found the performance of the 2 amps to be fairly comparable. Design 4 doesn't take the true difference of the quadrature signals, but instead amplifies a linear combination of the 2 inputs. Thus, the gain across the non-inverting path is not the same as the gain across the inverting path. R18 and R19 are included in some designs to make the system more symmetrical. However, they have no effect on the operation of the amplifier other than adding a little noise, so they are replaced with wire. Here's a table of the critical performance data for each of our designs as compared to the soft-rocked RX-TX receiver.
To prevent any heartbreak during the design and build process of your SDR receiver, we wanted to share with you a few tips and tricks we found very valuable. Tip number 1. Simulate your circuit first, then build after. This will save you tons of time and troubleshooting in the long run. The portions of the circuitry we highly recommend simulating are the mixer and amplifiers. We all used LT-Spice for our simulations, and a sample of what your receiver may look like being simulated in LT-Spice is shown here. This is my simulation, and I wanted to point out a few things to look out for when you do your own. First, looking at the outputs of the amplifiers. We are ultimately looking for two sine waves that are 90 degrees out of phase because that's what gives us our image rejection. Another thing to note may be the clarity and gain of the signal. If I click on the output of my second set of op amps that I'm using as a low-pass filter, you can easily see the difference between the signal before and after that low-pass filter. As mentioned earlier, there are many different topologies to choose from, but you have to be careful with your simulations based on the topology you choose. It may not only affect the final output, but also the output from the mixer. The output of the mixer should typically take this form, provided that no load is attached to the output. But if we attach our amplifiers, we get an output that looks like this. So it may seem like an incorrect and surprising result at first, but if we do circuit analysis on the differential op amps, we discover that this response should actually be expected for this particular circuit.
To streamline our design, my partner Jordyn Watkins and I decided to use surface-mounted components. To do this, we used a budget toaster oven to manually simulate a temperature profile to reflow solder paste and adhere our components to our circuit board. This allowed us to use cheaper components, create a smaller circuit board, and use components that have more ideal characteristics than through-hole counterparts. We were able to simulate the temperature profile by using a laser thermometer and the temperature dial on the toaster oven. By looking at the graph, you can see that we set the temperature to 325 degrees Fahrenheit for a minimum of 2 minutes to properly wet the solder paste. Then we can ramp up the temperature to be above 425 degrees Fahrenheit for up to 25 seconds in order to reflow the components. After reflowing the components, we can then open the toaster oven to quickly cool our device back down to ambient temperatures. This method proved to be very effective and repeatable in testing. It's important to mitigate ground loops in our designs, as ground loops can cloud the signals we are trying to listen to with noise. A ground loop is formed when there are two ground connections between a component and the ground plane. There are a few methods that we can do to mitigate this. Firstly, it's common practice to fill in all available circuit board space with a ground layer that serves as one reference ground. Another method to reduce ground loops is to add jumper cables that can isolate ground to one path by manually breaking the loops being generated. And finally, in design 2 and 3, we used a 1-to-1 transformer that was able to reduce our input noise by an additional 20 decibels. Using a combination of these methods in our designs yielded very positive results. When designing the board's layout, it's important to keep a few things in mind. It's a good idea to include a prototyping area on your first revision, as it's not uncommon for your circuit board to not work right out of the box. As previously mentioned, it's important to create a ground plane. In addition to this, it can be helpful to solder sockets onto many parts to easily change or replace components. It's important to separate digital from analog components, as the digital signals can generate noise on the analog signals we're trying to listen to. Lastly, test points. Being able to test and probe specific components on dedicated pins on one area of the board can make troubleshooting your design significantly easier. It's been the most useful addition of our entire design, and I would never design another board without them.
To sum it up, designing and building SDR receivers is fun, and what better way to advocate for electronic education and advanced radio technology than with something that is fun? We hope that the work we've done helps engage a larger audience in designing and building quadrature sampling down conversion SDR receivers.